So that was just sort of a generic look at explicit and implicit methods. Now let's talk about it in the context of elasticity problems. And here I'm only going to talk about elasticity and not poroelasticity in terms of the explicit analysis, because poroelasticity doesn't really lend itself very well to explicit analysis, because you're solving for, if you're solving a full dynamic problem, you need two derivatives in displacement, right? But you only have one derivative in pressure. So the second derivative in pressure doesn't exist. It's singular. And so to devise a sort of a very generic explicit method for that, it's just not typical. So we'll talk about it next time. We won't get to it today, but we'll talk about an implicit method for poroelasticity. But it's typically not solved explicitly. Also because the time scales of fluid diffusion and wave propagation are vastly different, right? So wave propagation is really fast, diffusion is really slow. And so, if you're taking your critical time step criteria due to the wave propagation to be 1 e to the minus 7th, you can't run your simulation long enough in a realistic setting to have very much diffusion occur at all. So it's just not done very often.
Yeah, but then we can use some other explicit time stepping method, like
Do what? Rungier-Kutta?
Oh, yeah.
Rungier-Kutta? Yeah. Yeah, I mean, it is possible. Yeah, it is possible. Because in Rungier-Kutta, you create a big first order system, right? And, yeah, it is possible. So I guess the explicit method that we're going to talk about here is a central difference method on displacement that allows you to compute the accelerations directly, right? So we're not even going to compute. We don't need the first derivative terms. We just need, so we'll actually compute them for the update, but we're not going to store them per se, right? We're not going to store the velocities. So yeah, you can do it. You can certainly do it. It's just not done very often. So we'll just talk about it in the context of elasticity here. And remember our finite element model for elasticity just looks like this. Or we might write it as where M is the consistent mass matrix. K and F is that. So nothing's changed there, other than the fact that up here in this equation, I wrote where this is the external forces, and this is the internal forces. Right? So remember, the stiffness matrix is like the resistance to deformation, so you might call that the internal forces, and this is the external forces. So, just some definitions here. We're going to assume that delta t at the n plus a half time step is t n plus 1 minus t n. And using that equation, so we just introduce a usually these increments, like delta t's, they live at the half time step. Because the right-hand side makes complete sense, right? We know the time at n plus 1 and the time at n. So then we're going to just define delta t at the n minus, at the n plus a half time step. Right? So it's just a definition. And then using that equation, then we can solve, or actually you could solve this equation and then increment by half a time step, or just simply introduce a new definition, however you want to do it. It says that t at a half is n plus 1 plus tn. So it's halfway. It's an average between n plus 1 and n time steps. So then with that, we'll say that delta t at an n is t n plus a half minus t n minus a half. Right. Yeah.
So for the F internal, is that really the case? I mean, or it needs a u somewhere in it. So like u of the previous step would be like, then it would be B transpose sigma.
Yeah, you're right. You're right. So it's ku. And yeah. Let's do it this way. It's this guy. Right. So with those definitions, we'll use a central difference approximation. So the first thing we'll do is we'll get the velocity. U dot, or the velocity at n plus a half, is equal to u at n minus 1 minus u at n over delta t n plus a half. All right. And so then u double dot at n, which is the acceleration at n, is equal to the velocity plus a half minus the velocity minus a half over t n plus a half minus t n minus a half. And that's equal to the velocity at n plus a half minus the velocity at n minus a half delta t n. And so then if we plug in this one into this equation, then we'll have an equation for the accelerations directly in terms of the time step and the displacements. So t n minus a half that's what you get. And if delta t is constant, meaning it's the same every time, right? Then this reduces to something that you're probably used to. But the reason this is, so both of these are, right, but the more generic form is because in explicit calculations, we usually get some, at every time step, we get some new estimate of the critical time step. Because it takes so long to run an explicit simulation, we always want to take the maximum time step we can get by with. We always want to be pushing the limit of what's stable, so we can take as big a steps as possible so we can get the simulation over with. And so what we usually do then is at every step, we'll compute an estimate to the stable time step, usually by some simplified sort of eigenvalue analysis. I say simplified, we don't really want to solve an eigenvalue problem. It kind of defeats the purpose of the speed of explicit. So we want to, but we'll do something to estimate the stable time step, and then we'll take the next step with that time step. So we're always changing the time step in an explicit simulation in general. Right? But if you wanted to just take fixed time steps, then you can just do this. That's your normal central difference second derivative approximation, right? So one last thing to point out is the mass matrix diagonal? Huh? No, it ain't. I wish it was. It's not. Right? Remember that it's going to have the shapes, it's going to have similar structure as the stiffness matrix. It's banded, right? Because you're taking the Ni, Nj. Remember that same operation, that sort of tensor product operation occurs in the stiffness matrix, right? So it's going to have the same structure as the stiffness matrix. It's not going to be diagonal. Which means that even though I'm doing an explicit calculation, if I use a consistent, the correct mass matrix right there, then I got to invert this stupid thing. And we don't really like to do that. So typically in an explicit calculation, we'll use something called a lump mass matrix. And there's really no good theory behind this stuff. It's sort of ad hoc, those lump matrices. But despite the fact that there's no real good theoretical justification for doing it, it does work for the most part. It works pretty well. So basically what we're going to say is we're going to say that we're going to build a diagonal mass matrix. Because if we have a diagonal mass matrix, the inverse is just 1 over the entries, right? It's not really inverting a matrix. So with the diagonal, we're going to basically say that the diagonal entries are the sum of the consistent mass matrix, the sum of the rows of the consistent mass matrix. Or, typically we're not going to, since all we want is the diagonal entry and we only restore the diagonal entry, we're not actually going to say compute the entire consistent mass matrix and then sum up the rows. You just sort of do it in one step, and so that the diagonal mass matrix is like that. Well, if we have a partition of unity in our shape functions, which we do, then that summation term is just 1. So then there's something like that. So let's just go over a flow chart for explicit analysis. So the first thing we have to do is initialize everything. Right? So we're going to initialize the initial velocities, any background stress you might have, the initial displacements. N is equal to 0, T is equal to 0, and we're going to compute M. So if we're doing a total Lagrangian simulation, and what we mean by total Lagrangian is, remember, if we go back to finite deformations, we're going to solve everything with respect to the reference configuration. Okay? Now there's also something called an updated Lagrangian, which essentially in an updated Lagrangian, every step you take, or every solution you get, you update the reference configuration. Right? We can show that they're actually equivalent, doesn't matter. But the benefit of doing the total Lagrangian is that we only need to compute the mass matrix once, up front. Right? And for that matter, even its inverse. Right? If you wanted to use a consistent mass matrix, you could just compute its inverse up front.
What is the benefit of the updated one?
If you really have all finite deformation theory, I don't know that you can claim that there's a benefit. If you're trying to fake finite deformation theory with small strain theory, then there would possibly be a benefit, but you can still get in trouble if there's rotation. Because remember, finite deformation theory is geometrically nonlinear. So even if you have linear constitutive models and other things, forget about plasticity. If you have large deformations and rotations, you still have nonlinearity just from geometric effects. And those come out from those extra terms in the strain tensor that we ignore in the small deformation theory. Anything that's nonlinear, you can think of as linear on the fly, right? If I linearize and take a step, and then I linearize and take a step, and then I linearize and take a step. It's sort of how we do even nonlinear through Newton iteration, right? So you could sort of fake or get an approximation to the geometric nonlinearity using a linear model and doing an updated Lagrangian step. But rotation would still bite you. So if you have a true finite deformation theory, I don't know that there's a benefit. That's also sort of assuming that your deformation is not so bad that your mesh gets really entangled, that you really deform the element so much. Right? If you had that much deformation, then you would certainly have to do, the thing to do there would be to do a remesh, right? So at some point, you've really distorted your element so bad that your integrations are bad, maybe you have negative Jacobians, then you can stop and you can remesh, right? Fix your mesh and clean it up, and then make that your new reference configuration. The problem with that is that if you really have that much deformation, you probably have plasticity, and you have internal state variables associated with the plasticity. Your external state variables remember, they're carried in time, right? Equivalent plastic strain accumulates. Where do they accumulate? At the integration points, right? Now you remesh and you've got new integration points that aren't where the old ones were. So you have to do some type of advection process or remapping to sort of an averaging, if you will, but a smart way to remap those internal state variables. And sometimes that can introduce errors. So I prefer, a total Lagrangian approach with a caveat that we're not going to have deformations that, if you have such large deformations that you really entangle the mesh and other things, I would suggest probably using a mesh-free method for that, which we're not even talking about in this class. So that's a long-winded say that your question was, what's the advantage of an updated Lagrangian? That was a long-winded way of saying probably not one. Just do the finite deformation theory total Lagrangian. So you're going to compute F0, which is your external forces minus your internal forces. You're going to compute your accelerations then at step 1 is the inverse of the mass matrix times your initial forces. You're going to update time. And your half time. With your half time, you can update the velocity. Like that. You're going to enforce the boundary conditions on velocity. So what we mean here is, we just computed a new velocity. We just computed a new velocity based on the half time and the accelerations. But we may have velocity boundary conditions. We may be driving the simulation by pulling on the edges or something, right? And in that case, you don't want. So you need to sort of override those velocities, those nodes that have prescribed boundary conditions. You need to override them. Then with that, you can then compute your new forces and your new accelerations. And then you might want to, you can skip this step. You can skip this last 2 steps, but it might be a wise thing to do is to update the velocity to the full time step, right? We use the half time step velocity to update the accelerations, but it might be wise to update the velocity to the full time step, and the reason for doing that is so that you can check the energy balance. Specifically, look at the kinetic energy, which is 1/2 m v n plus 1 v n plus 1, right? The telltale sign that you have an unstable system is the kinetic energy blowing up, increasing, right? It should always, at a minimum, be constant, but it really should decay with time. So, as it goes into potential energies, it deforms the system, right? The kinetic energy should drop. It should never increase. And then with that, you can cycle back to 4 and take another step. All right? I sort of went over, so